You know, when you look out your window, the world probably looks pretty permanent, right? A mountain is just a mountain, a valley is just a valley. Well, welcome to today's explainer because we are going to completely shatter that illusion. We're exploring the Earth not as some static, dead rock, but as a living, breathing, and wildly dynamic machine. From the microscopic grains of dirt right beneath our feet to the massive, slow motion bounce of entire continents, we are going to decode the secret physics of the landscape.
It really brings up a profound question. Are mountains just static monuments, or are they constantly moving machines? See, for the longest time, geographers viewed landscapes simply by their history, basically how they slowly decayed over millions of years. But modern geomorphology, it views them as highly active systems. Every single grain of sand, every drop of water, and every sheet of ice is part of this massive interconnected web that is constantly reacting to the forces around it.
All right, part one, the landscape as a system. We're talking about a true geomorphic revolution.
This shift in thinking was huge. Scientists began looking at landscapes as operational, functional units instead of just decaying chunks of rock. We used to think about landscape evolution as progressive, linear decay, just a valley floor slowly wearing down to nothing over 10 million years. But then, researchers like Shum introduced this brilliant concept of dynamic metastable equilibrium. The landscape doesn't just smoothly wear away. It constantly adjusts itself. It experiences episodic erosion, dropping in sudden, dramatic steps, and then it self-corrects to maintain a stable form over shorter periods. It's absolutely fascinating. The landscape isn't just dying, it's actively seeking balance.
And that brings us to a foundational idea, summed up perfectly by geographer D.R. Stoddard back in 1967. Basically, the Earth acts just like the thermostat in your house. When a landscape starts eroding way too fast, negative feedback mechanisms automatically kick in to slow the whole thing down. For example, a rapidly eroding hill might shed a bunch of rocks that eventually pile up at the base. Those piled up rocks then protect the lower slopes and stabilize the whole system. The living Earth naturally prevents its own runaway destruction.
Moving on to part two, unlocking particle secrets. It's time to zoom way, way down to the microscale.
To truly wrap our heads around these massive landscapes, we literally have to get down into the dirt. Let's talk about two fundamental terms geomorphologists use when they analyze soil and sediment: shape versus sphericity. Now, you might hear those and think, yeah, same thing, right? Actually, no. Shape simply describes what a particle looks like. Is it a flat disk, a long blade, a roller? Sphericity, on the other hand, is a much more functional metric. It measures how much a particle deviates from a perfect sphere, and it's specifically based on how fast that particle will sink in water. Why compare it to a sphere? Because for any given volume, a perfect sphere has the absolute least surface area. It offers the least resistance as it falls, meaning it maximizes its settling velocity. So sphericity isn't just about looks, it is a strict mathematical predictor for how rivers transport and drop their sediment.
Part three, the physics of soil and the immense stress on the mountain.
So how do we figure out how these tiny, microscopic particles behave under the crushing weight of a mountain slope? Well, scientists literally bring the mountain into the laboratory. To find a soil's breaking point, what they call its shear strength, they follow a very specific process. Step 1, they pack a sample of soil into a specialized split metal box. Step 2, they pile a heavy load on top to simulate the massive crushing weight of the earth above it. And finally, step 3, a motor-driven ram slowly shoves the bottom half of the box sideways until the dirt literally rips apart. Picture that direct shear box setup. We've got the soil sample trapped right in the middle. The top plate is completely locked in place, pushing down to apply normal stress, while an outer water-filled box lets researchers perfectly control the moisture level. Then, a yoke forces that bottom plate to the side, shearing the dirt sample right down the middle. This highly controlled destruction is exactly how scientists calculate how much force a hillside can take before it violently collapses.
Okay, part four, when mountains move, let's look at real-world soil failure. Let's pull our perspective back out to the actual hillside. Back in 1964, a researcher named Skempton made a massive breakthrough using that exact shear box machine we just talked about. He discovered there are actually two totally different types of soil strength. You have peak strength, which is the absolute maximum resistance that dirt puts up before it snaps for the very first time. But, and here's the crazy part, if you keep pushing the dirt after it breaks, the resistance drops dramatically to a much lower level. He called this residual shear strength.
The real-world implications of this are terrifying. It means old, dormant landslides that fell maybe hundreds of years ago are permanently weaker. They are essentially hidden traps. It takes significantly less force to reactivate an old landslide than it does to trigger a brand new one. To mathematically predict these kinds of disasters, scientists rely on Coulomb's failure law. It's essentially a balancing act between the forces trying to pull the slope down and the forces holding it up. The downward weight, the friction of the rock, the sticky cohesion of the soil, they're all vital variables. But I really want to draw your attention to one crucial factor: pore water pressure. When heavy rains soak a hillside, water fills the microscopic pores between the dirt particles. This trapped water physically pushes the soil grains apart, dropping their friction to practically zero. Coulomb's law mathematically proves that a sudden spike in this hidden underground water pressure is almost always the invisible trigger for a massive, catastrophic landslide. Section 5. The weight of ice. This is where we look at the Earth's bending crust.
Now let's zoom all the way out to the macro scale to witness how truly enormous forces can literally bend the planet's crust. To understand this, we have to look at the theory of isostasy. This is the idea that the Earth's solid crust essentially floats on the denser, fluid mantle below it. Historically, you had scientists like Airy who believed the crust floated because mountains had deep, iceberg-like roots. Meanwhile, Pratt argued it floated because different blocks of crust simply had different densities. But either way, they both agreed the crust is absolutely buoyant. So think back to the last ice age. Massive, impossibly heavy glaciers covered huge chunks of the globe. That weight physically pressed the buoyant crust deep down into the mantle, like a person sitting on a really squishy mattress. When the ice finally melted, all that weight was lifted, and this causes what we call isostatic rebound. It's the gradual, delayed upward bouncing back of the crust. The wild thing is, the ground is still rising today, thousands of years after the ice melted. It totally proves our planet's surface is flexible and constantly trying to find its equilibrium.
If we look at historical data from places like southwest Sweden, specifically the incredible research done by Murner back in 1971, we can see this massive rebound in action. He tracked shore level displacement over thousands of years. The land that was located closest to the absolute center of where the heaviest ancient ice used to sit, it literally shot upward after the melt. It rebounded the highest and the fastest. Meanwhile, the land much farther away from the ice's center barely moved at all. It is an unbelievable visual record of the Earth slowly exhaling and expanding after being crushed for millennia.
And finally, Part 6, Geography for Our Future and its Service to Society. So why does measuring microscopic soil grains or charting continental bounceback actually matter to you and me today? Because this is geomorphology in the service of society. We aren't just looking at dirt and rocks for the fun of it. By understanding exactly how soils fail at the microscopic level, we can predict exactly where deadly landslides are going to strike, literally saving entire communities. By mapping out ancient landscape changes and knowing how rivers will reactively adjust their sediment over time, we can safely engineer dams, plan regional developments, and make sure our infrastructure doesn't just get washed away. Understanding the Earth as a dynamic, interconnected system is absolutely crucial for keeping all of us safe.
I want to leave you with this final, provocative thought. We've seen today that the Earth is a living machine. It's carefully balanced by negative feedback loops, and it can take thousands of years to bounce back from major events like an ice age. So, if the very ground beneath our feet is still reacting to the heavy ice of the ancient past, what future geographic chain reactions are we setting in motion today? The landscape never stops adjusting. Thanks so much for joining me for this explainer, and remember, keep questioning the world around you.